Few minutes if you want for people to file in.
Good afternoon, everybody. Can you hear me? Is this on? Yes? Okay. I talk very quietly. I apologize. As you're coming in, there is coffee and tea and water off in the alcove over that way, if you need some. And otherwise, I think we are ready to get started. Welcome to the last, or rather fourth, because hopefully we will be doing some more of these Gen AI tutorials soon, but our fourth in a series of tutorials that Midas and the AI Lab have been putting together, called Making Generative AI Better for You, Fine-Tuning and Experimentation for Custom Research Solutions. And I am thrilled to welcome Shane Storks back to our stage, who was instrumental in helping us put together a great faculty Gen AI workshop this summer. Also had a really nice presentation, and I'm really excited to hear more from you today. So welcome, and I'll let you take it away.
Thank you, Beth. I guess I want to figure out what's the right distance from the mic. Can you guys hear me okay right now? Okay, so I don't have to lean super forward. Yeah, so first of all, I guess you might be wondering if you RSVP'd or saw this event online. Joyce Chai, my advisor, was supposed to be leading this lecture. Fortunately, she's not feeling well, so I'm taking over for her for both parts of today. But I am the next best thing because I'm her sixth year PhD student. So yeah, hopefully I can do a good job and teach you a little bit about how to customize LLMs and generative AI for your own research solutions. Oh, and by the way, I'm a PhD candidate in CSE. I mainly am in the AI lab. So that's where you can find me usually, is on North Campus. Also, please let me know if if you ever can't hear me. So, oh, I can just, okay, perfect. Cool. Still sound good? All good? Cool. All right. So I guess I don't need to tell you this if you're already here, but I think a lot of us know that LLMs, large language models like ChatGPT and GPT-4, they've recently become super, super popular due to their impressive language understanding and reasoning capabilities. We use them as assistants for a lot of different language tasks. For example, it might be a bit hard to read with like the dark mode up here, but for example, I can copy the web page about these tutorial sessions and ask GPT-4, what's the next session? What do I need to know about it? And it can easily do that. And you can use it for a number of writing, coding tasks, and so on. But what we're going to talk about today is how can we customize LLMs like these and apply them to sort of empirical research. I guess first I wanted to say a few words about, well, what really is the role of LLMs in research? I think we do know that they can be helpful assistants for tasks like writing or coding, and, we do a lot of that in our research. I think a lot of us do. But then they could also be useful to automate aspects of like data annotation, for example, domain-specific content generation. I've had people come to me and ask about, hey, I need LLMs to help me design a battery or something like that. So sort of domain-specific content, you might be able to customize them to be able to do this. And really any language-based applications, you might get some luck using LLMs, trying to apply LLMs to them. However, they might not perform well at specialized tasks like these ones I'm talking about right out of the box. So we want to know, how can we customize LLMs to adapt them to various specialized language tasks? And before I move on, I want to also shout out the Midas Using Generative AI for Scientific Research user guide. That's a QR code to it. I'm sure these slides will be posted later, and you can just find it on the Midas website. It's very helpful to give you some ideas about what you should and shouldn't use these LLMs for in research. And I'm also going to share some thoughts about that as well. Yeah, so this is the outline for today. Not too many things, but we'll start with sort of a quick road on how did we get to these LLMs. And I don't want to give like this huge AI lecture, but I do want to go over some key developments that kind of got us to where we are now, so you understand like the characteristics, the key characteristics of these systems. So first, I guess let's just go over what is a language model in the most general terms. You could say it's just basically a distribution, a model of the distribution of language. Basically, we're modeling what is the probability of some word occurring after some other sequence of words. We're trying to basically make this model of sequences of words. So most language models you'll be seeing and using nowadays would use a model like this to basically learn what is the distribution of language. And for example, I guess what can we do with this? This seems kind of simple, but we can do a lot with it because we can basically use it to generate language, given some language inputs, or we can use it to judge how likely is some sequence, some text, some sequence of words, right? So for example, given this incomplete sentence, Jack needed some money, so he went and shook his piggy blank. As humans, we can possibly anticipate what the sort of the next word will be here. But in a language model, we kind of can just calculate this by prompting it with this incomplete sentence. And at the low level, language model can give you a probability distribution of all the possible words that could come after the word piggy, right? And through that, we can probably be pretty confident that the next word should be bank. So based on this simple objective of modeling what is the next word in language, and basically training deep neural networks on essentially all the text on the entire web, today's state-of-the-art large language models are useful for just about any language task, just from this sort of model of what's the next word. So, this sense of a language model, by the way, it's been studied in language technologies for like speech recognition and machine translation as far back as like at least the 70s. But the evolution, just from the simple idea of modeling the probability of the next word to today's LLMs, this was due to a number of key developments. I'm going to try and cover the last 10 years of these developments very quickly to give you some high-level ideas about, what are these key characteristics of LLMs that makes them successful. And then we'll also cover how these contribute to their key limitations. And once we have sort of this good sense of how these LLMs work, then we can get into really how are we going to customize them for our research solutions. So let's see. Oh, by the way, I guess I missed this. If you wanted to calculate the probability of a whole sequence of words, you can do it using an equation like this. Basically, the probability of this whole sentence is approximately equal to the probability of bank given previous words times probability of piggy given previous words, and so on. And this probability is modeled by your language model. So if none of this makes sense, that's okay. I'm basically just trying to really hammer home that these things are models of what is the next word. So one key development that helped us get to where we are now is the idea of pre-trained vector-based word embeddings. These started happening around 2013 with Word2Vec and Glove, they were called. And in short, the idea of these approaches was, well, if I train a neural network similarly to a language model, modeling what are the words that are around other words, if I can do that, then the learned weights I get for different words in this neural network can become transferable vector representations that somehow capture the semantics of a word. And more semantically similar words are pushed closer together in the vector space. So you might see, for example, we have all these words like doctor, nurse, hospital, egg, omelet. We would see after training this word embedding, we end up with words that tend to appear closer together in language, tend to be closer together in vector space. And this is kind of trying to capture the semantics of these words, right? Because these words also are quite similar in meaning. And I guess one cool thing about these things that people have been fascinated by since the early days is these word embeddings exhibit like powerful analogical compositional properties. For example, we might find that for related sets of words like gendered nouns, like man, woman, king, queen, or like verb tenses, walked versus walking, swam versus swimming, if we look at the difference between the vectors for those words, it's actually quite consistent. For example, the difference between king and queen is the same as the difference between, almost the same, as the difference between the vectors of man versus woman. So we have these sort of vector representations that have some nice properties to them. They kind of have this compositional nature, and that's kind of thought to be a key characteristic of human language. So we really like that. So now, through this, we have some kind of numerical representation of language. On top of that, we also need to have a representation of, sequences of words. A language model needs to be able to represent not just single words at a time, but also sequences of words, right? So neural networks for representing sequences of data, which are called like recurrent neural networks traditionally, had long been studied before this for all kinds of domains, like in machine learning and AI tasks. But around 2014, we saw a lot of people trying to apply recurrent neural networks for language modeling. And the idea of these, I'm not going to go too deep, is that we want to represent each input word. For example, so long and thanks for. Each input word, like the word thanks, we want to represent it not only informed by some pre-trained input embedding, but we also want to incorporate the embeddings of the past words. So we use neural networks to kind of mash all these representations together so that now every word is kind of represented based on the sequence of words that came before it. So this was a development. This was good. It helped us make some progress on like AI-based language modeling, but these models here are so computationally expensive, and also they kind of have some issues of like forgetting information from words as it processes more words. And then if you have a lot of text you're trying to process, that becomes a problem. So then I guess what we did to try to solve that was attention. Basically, this was the idea that was originally implemented for machine translation, and at a high level, the idea of this is we can allow neural networks like LLMs to learn implicitly what parts of the input text can best inform the generation of each word. So in general, right, this sort of ability allows us to robustly get the most relevant information from different parts of the language context as we generate words with a language model. So this kind of solves this problem of being able to forget things as we're processing more and more words. And this was important because up until this point, all the language models are representing language only from left to right. So it was just super easy to kind of lose long-range information. And now, today, if you use like ChatGPT or GPT-4, you can give them a ton of information and it can capture things from all kinds of long ranges. Now, specifically, though, because this might not make any sense yet, in machine translation, the cool thing about this is that this enables to better handle when, the target translation, we're trying to translate to some other text, right? This helps us handle when a translation would have a different word ordering than sort of the input source text you're translating from. So in this example here, we can see we're looking at sort of the attention, how much is the model learning that different words are important to each other. We're looking at the attention as we're translating French to English. So for example, the French word for European has high attention on the English word, or is attended highly when generating the English word for European, even though these words are in different orders, right? European is in a different position in this English sentence versus this French sentence. So this idea of attention was very important to be able to really robustly handle word ordering and long-range dependencies between words. And then, okay, now we're getting more recent. The ideas was really taken to the limit in this well-known paper that was called "Attention Is All You Need," which proposed transformers, which was a neural network architecture made entirely out of attention mechanisms like this, entirely out of layers that are just trying to learn what information can I extract from the previous information. This probably looks quite complicated. I'm not going to go into all these different pieces, but really the key insight that we had was that these transformers now have all these attention heads, and basically these individual modules that are running over the language and trying to pull out information. And then we're kind of implicitly learning how to pull out the information and when. And ultimately, this also enables us to represent each word in the text as a function of all the other words in the text. So now, rather than processing language in some kind of left to right sequence like these RNNs were doing, we're kind of processing all the language all together, looking at all kinds of possible dependencies. So these things are just getting more and more powerful. In fact, transformers were also much more computationally efficient. You can parallelize them when you train them, and this just made suddenly a lot of new things come about. So one thing we saw was contextual language representations. So the idea here is, when I first talked about word representations, vector representations of words, the problem was each word has one representation. Like the word play maybe has one vector to represent it, even though play can have many different senses. Play could mean something like a move in sports, or play could mean something like a theater production. So we started working on representations of words that really were dictated by the other words around them, was one key thing. I guess, let me see here. So we have this idea, we have transformers. What happens when we combine them and also throw a bunch of language at them? We start getting these sort of transformer-based LMs that really start to impress people. So around 2018, this was like my first semester of grad school, this model called BERT came out. It was this transformer-based, encoder-only language model that you could basically fine-tune to all kinds of tasks. I guess it was so impressive. Suddenly, these language models were everywhere because you could apply these things to anything. Where does that capability come from? Basically, it's this idea of self-supervision. We actually started training these neural networks to reconstruct their language input. So say we're given this earlier sentence about Jack needed some money, he shook his piggy bank. If we want to mask out a word here, we can then train a language model to sort of predict that word. And if we do this at scale, we mask all kinds of tokens, and iterate over all the data on the web. Ultimately, we start getting language models that look quite like the ones we have today. And I already started talking about this idea of transfer learning in these language models. So this is something we're going to actually do hands-on today. So the idea is, once I've done all this training of a language model on all this language data from the web, I can then take it and then train it a little bit more on some other tasks. So I have BERT, which is this general purpose language model, but it's not perfect. So what I want to do is then add some extra classification or task-specific layers on top of it, like here are some examples of task-specific things you might plug into these language models. If I want to tackle multiple choice question answering, I have a possible layer to do that with. If I want to tackle similarity between sentences, I have a way to do that. So the idea is I plug in this extra layer, train it a little bit more on some specific task, and now I can get super high performance on this downstream task. And this was surprising because up until now, like language understanding as a whole was still like a very complicated, difficult problem with a lot of unsolved challenges. And suddenly we're seeing like all these amazing near human level results. So I guess because I'm going through so much dense stuff all at once and I need some water, does anyone have any questions at this point? Cool. So And by the way, it's okay if this doesn't make much sense to you. I think what I'm trying to really give a sense of is where did these come from? What are their characteristics? What are really these key things about them that have made them so good? And these are what they are. So then after we had BERT, it was this big moment, and there was kind of this crawl of bigger data and bigger models, meaning more and more learned parameters in these language models. We're using we're using more and more parameters to try to learn this distribution of language. We found, as you may or may not be able to see very well in this graph from Microsoft, we found that so this model called BERT has maybe like 100-something parameters. It's like it's at the low level of how big can these models get, how much information is encoded in them. But then over these few years, suddenly the growth was exponential. We were training models that were in the tens of billions of parameters. So as these models got bigger, we found more and more data to train them on. They just kept getting better and better. And yeah, we were seeing uncommon language understanding benchmarks. Here's some examples. You don't need to remember them, but these are just some common evaluations that people would apply their language models to, called SWAG and GLUE. And the idea was, let's see how well the language model can understand language, and sort of like a common evaluation that we could compare all these language models with. So as you could see, human performance for these two tasks is like these dotted lines. And through these few years of getting bigger data and bigger models, human performance is just getting exceeded on these benchmarks and so many others. It's kind of got us to the point where language models are so good that it's hard to really evaluate them now, because they're solving all of our benchmarks that we've spent so long building. Yeah, and I guess it's worth noting too that this is kind of where we started saying large language models instead of just language models, LLMs instead of LMs. I'm going to use them mostly interchangeably today, but this kind of gives you an idea of where LLMs came from. And as that happened, soon it became the case that we no longer had to train them on specific tasks, and they became very easy to use. In fact, we could just do some kind of zero-shot application of these models to downstream tasks. Like say we want to translate English to French, we could just take GPT-3, which was the new language model at this time, and ask, translate English to French, and give a word, and it can output something for us. No training data needed, just apply it directly. However, this wasn't always perfect, so it was also beneficial to do something called few-shot in-context learning. We're going to play with this hands-on, so it's okay if it doesn't quite make sense yet. But the idea here is I'm not going to train the model. I'm not going to update the internals of the model by training it on all this data, but I'll just give a few examples of what is the task I want it to do. So if we're still translating English to French, let me give a few examples of what I mean when I want you to translate English to French, and then ask for what I want to ask. And this can improve the performance in these models, actually. So suddenly these things were getting very, very good. This was another huge moment in NLP as well. Suddenly, again, more tasks, even the new harder ones we had built, were being solved by these models. And the largest models were even the best at this. However, now these models are getting so large, they have so much knowledge about this distribution of language encoded in them, so many parameters, so many layers. It's hard to actually host them on your own computers, your own machinery. So because of that, OpenAI, which is the company that made ChatGPT and GPT-4, they start providing paid APIs to prompt them and fine-tune them rather than you having to do that yourself. And we'll talk about the pros and cons of that later. So another development is what was called instruction tuning. And this is basically the process of fine-tuning language models on a variety of tasks to make them better general-purpose problem solvers. So for example, maybe we take a few existing data sets for question answering, for machine translation, for a few different things we might be interested in using the language model for. and we train it on all of those things. In fact, once we do that, it can become really good, even on some tasks you didn't train it on. So this was one idea. Then there was a sort of a more developed idea where we used reinforcement learning from human feedback annotations, or RLHF, and we are able to actually learn sort of a policy for general purpose assistance through language models. And this sort of thing, this what they call reinforcement learning from human feedback, is what gave us ChatGPT around the end of last year. So now, with all these different little bits and pieces that we've gathered over the last 10 years, right, we've gotten to these incredible general purpose LLMs that we can use for so many different things. This is where a ton of attention was starting to occur from the public and other research disciplines, and it's possibly why you're here now, is this sort of where we're at this point. It was also worth noting that there's been an increasing emphasis on incorporating images and videos into what are called multimodal LLMs, and they're capable of representing and communicating about visual and text inputs together. While this effort, it happened in parallel through like this whole development of LLMs, people were also working on image understanding, video understanding, and all of that. Some of the recent models that we've seen that have been really good at this, like GPT-4, who you now can put images into GPT-4, right? They've had the biggest successes in doing this and creating machines that can do really good reasoning about images in zero-shot settings. You don't have to train it. Just drop an image into GPT-4 and start talking about it. So while most of the implementation details of GPT-4 haven't been shared with the public, it's thought that it's powerful just because it's training on both images and text all together. So this sort of idea of multimodality is maybe also considered one of these key developments that got us to where we are today. My lab and Joyce's lab is called Situated Language and Embodied Dialogue. So we're very interested in this direction of the multimodal LLMs, and a lot of our ongoing work is like looking at how can we apply them to different problems in various domains where we both need to see and speak, communicate with AI systems. So yeah, I guess there's your crash course in history of how we got to LLMs. Beyond that, I guess I just want to kind of give you a quick landscape. I'm going to show you a very complex looking slide. A quick landscape of all of these LLMs that are out there now after all these 10 years of development. So you can see, the last several years have had a huge explosion of all these different systems. There's basically each node on this tree is another type of LLM that someone made. And they do have some key architectural variations that I don't want to get terribly into. You might see that this tree is talking about encoder only, encoder, decoder, and decoder only. And since you might see that jargon a lot as you're playing around with LLMs yourself, I might as well explain it a little bit. So some LLMs are encoder only, which means they're basically just trying to represent language. That's their main purpose. They're not necessarily focused on generating language. Some earlier language models like BERT that I talked about were encoder only. Some are encoder and decoder, meaning they might have separate modules for representing and generating language. So this can make them especially adept at tasks like translating languages to one another, because they can simultaneously have a representation of what language you're putting into them and what are you going to output. So then there's also really what's the most popular now is like these decoder-only language models, like GPT-4, I believe, is an example of one, where really they're just trained only to generate language. That's their main goal. They're not trying to learn any kind of representation of the input that's different. Everything is going toward generating language. And really, the key difference that matters here is that this is the most efficient way to learn these language models is this decoder only, and that's where the biggest explosion is that's what everyone's doing now. And depending on the type of task you're working with and sort of your hardware restrictions, do you have GPUs or whatever you have access to, you might find yourself leaning one way or the other on which of these types of architectures you might want to be using. I guess I've talked your ear off about the history of LLMs, so hopefully if nothing else, you got some insights about how they work at their core. So, because I guess next we're going to talk a little bit about their limitations now that we're impressed and we've seen all these cool things about them. Are there any questions at this point? Yes. Right. So the question is, can the large language models translate from English to, non-Latin languages like Chinese or Russian or, and I'm not the best person to ask about this. There's a lot of work in NLP on like multilingual language models. I think ChatGPT and GPT-4 maybe can do a little bit of a good job, depending on how many resources there are for your language. If you have a very rare language that there's not much data for online, it's probably worse at that. But yeah, now the LLMs today are kind of trained on like all kinds of languages. You could ask ChatGPT to translate to Spanish. Maybe it'll do a pretty good job because there's a decent amount of resources out there for Spanish. But yeah, I haven't worked much with like multilingual stuff, so I can't say too much details, I guess. Any other questions? Yes. Yeah, so I guess the question is about like the hardware restrictions for these models. Are they maybe specific to models? Can some run on CPUs, whereas some require GPUs? So I guess that is like that's like a pain point when you're doing research with these things, is having enough GPUs to be able to run these things. Now, these earlier approaches like Elmo, like Glove, you could probably run these on like your laptop and it's fine. But then, like, as they've gotten bigger and bigger, we have like BERT, these earlier models up to like 2020. You probably need a GPU to use them efficiently. Otherwise, they'll be very slow if you try to run them on just like a CPU or multiple CPUs. Meanwhile, if you go to like today's language models like GPT-4, I don't think any of us have access to the amount of GPUs, the number of GPUs that you would need to host that and run it yourself. So, this sort of issue of how much hardware do I need for my application or what's possible with the hardware I have, that's something we'll go over a little bit in the sort of the hands-on second half of this for sure. It's a whole thing, yes. Any other questions? Cool. So now we'll move on to sort of limitations. So I just talked up these things a lot, right? But I guess having seen all of this rapid growth in my PhD in these of these LLMs, I'm like very aware of also their limitations. So it's like, yes, we've had all these advancements. They're very impressive, but then there are still some undesirable behaviors. And if we want to apply them in our research, I think it's best that I also talk about these limitations, right? Because in order to effectively and responsibly apply them in research, we should be mindful of the limitations. So the first one we'll talk about is what I'm going to call spurious cues in language data. So when it comes to fine-tuning language models, this was a very pervasive problem, but it can still kind of occur if you're doing in-context learning, if you're prompting language models as well, if you're not careful. So the idea is this, a lot of times we want to apply language models to language tasks and let them basically read some text and make some predictions about it. For example, let's say we have this story about Karen and her roommate, and this is just a benchmark from the NLP field. This isn't really necessarily a real-world task, but say we have this story we want the language model to comprehend. We might ask in this benchmark setting, how does the story end? We have two choices. Karen became good friends with her roommate, or Karen hated her roommate. So we as humans, I think it's probably pretty easy for us to determine the answer. We are going to infer that Karen became good friends with her roommate because, okay, the roommate and her, they went to a concert, the show was fun. And these are the sort of cues that we'll use. It's like actual words, actual information from this text that contributes to our prediction. But if I'm going to apply some kind of supervised learning on a language model to solve this task, what can happen instead is something a little bit different. Instead of looking at important cues that might tell us actual information from the text, language models might be more likely to latch onto very spurious artifacts in language data. For example, there was a paper, I think I cited it here. There was a paper that looked at this specific task and trained some language models, fine-tuned some language models on it, and found that language models aren't really looking at the same information as humans. In fact, they might just see the word hated in one of the endings and say, well, there's no way that could possibly be the right ending because when I was trained, all of the wrong endings had the word hated in them, or something like that, for example. So because these models are sort of statistical pattern recognition machines at their core, you always have to be aware of when that could come back and bite you when you're trying to apply them to tasks. Yeah, I guess if you are fine-tuning language models, which we're going to do today, once you do this and your model is latched onto these spurious cues, if you try to apply to some other related data, apply to some other related task, try to generalize to something new, it's probably going to struggle a lot because these cues tend to just be kind of data set specific, something like that. So we really want them to do more human-aligned reasoning, like based on the correct cues. In fact, my PhD research is really looking at this issue. I mean, this is what I've been studying a lot. So another issue, though, is data contamination, which is kind of like the updated version of this for when we're prompting LLMs. So LLMs have seen so much data in pre-training. In fact, they might have been trained on different benchmark data sets we're using to evaluate them and gauge their capabilities. And I think I've already kind of hinted at this. If any of us have taken any like machine learning or data science courses, training on the test data is not going to be an objective evaluation. So now that these LLMs have seen everything on the web, we kind of are facing this question of how do we really gauge the capabilities of these models? The GPT-3 paper actually was one of the first to start looking at this issue in LLMs. So they basically wrote a section. They said, our training data for this model was sourced from the whole internet, and it's possible that we accidentally took some testing data from these different benchmarks we used for evaluation. And in fact, they went on to do a whole detailed analysis and found that several of their evaluation metrics on common language understanding benchmarks were kind of flawed because they had taken test data from those benchmarks and trained the model on them. But then they said, well, we already spent millions of dollars training this model, so we're not going to do it again, but we'll put an asterisk next to these results because that's the best we can do. So when papers and headlines, when you see people talking about, oh, LLMs, ChatGPT is better than humans at X, Y, or Z, or, ChatGPT passes the bar exam, we do have to question the contamination of the LLM's pre-training data to really objectively evaluate whether progress is being made. And yes, this is a developing area of research, and while we still can't deny these things are very useful and smart in so many cases, got to keep this in mind, right? So another issue will be interpretability of these models. So we do have to remember, and this might feel very abstract if you're kind of new to this sort of area, but these models have a lot of learned parameters, meaning basically when you put language into GPT-4, there are maybe I think it's rumored that there are over 1 trillion different calculations being done on top of what you put into the language model. So because that's happening, it's now becoming kind of opaque. How are conclusions made in these models? And therefore, it becomes hard to disprove when models are generating language based on spurious information, based on memorizing the training data and the pre-training data being contaminated, or on the other hand, if they're showing some kind of true human-aligned understanding. And it's hard to really tell the difference a lot of the time, but it's something we have to keep in mind. And another thing that's sort of compounding the issue here is that like GPT-4 and the newest LLMs that are out there are closed source. And by that, I mean, we can't even look inside of the box. We can't inspect the internals of these models at all. They don't release any details about them. They just give you this website that you can chat with or this API that you can call. So because they don't really give any details about the model architecture, or anything about the model, it starts becoming harder to use them in research because we have to really understand what factors of these models are leading to the performance we're getting. But before I digress too much, I guess interpretability is also an issue. And then the last one I'd like to say a few words about, which you may have heard about as well, is hallucination. So hallucination is kind of a broad term that really just means whenever we're trying to generate text, but it's factually incorrect, it's nonsensical, or it's somehow unfaithful to our inputs, or otherwise incoherent. That's a very broad definition because people are using it for a lot of different things. This can take a lot of different forms, but the general message is that you can't trust LLMs to be factual or coherent. For example, if I ask ChatGPT about Joyce Chai, here's what it tells me. It might tell me something like, it says some reasonable things. It says she's a professor in the Department of EECS here. That's correct. But then it says, oh, she's working on sentiment analysis and emotion recognition, which I'll have to ask her sometime, but I don't think that's quite as representative of what she's working on. And then really interestingly, it says she got her PhD from the University of Washington, which is just flat out wrong. She got it from Duke, I believe. So I guess the problem that happens here is we really can't trust the outputs of these models to be factual. We have to double check them. In fact, not everyone has done that and gotten in legal trouble. Like I think earlier this year, there was a headline about a lawyer citing some fake legal cases that were generated by ChatGPT in their legal brief. And yeah, we can't do that. We have to double check. So in summary of these limitations, I guess we know that, again, LLMs are remarkably useful for so many language tasks, but these limitations do make them very hard to trust consistently. So verifying LLM outputs is important. We have automated metrics and benchmark evaluations to do this to some degree. Human evaluation is also important if you're doing something that's very high impact, like writing a legal brief or something like that. I guess my main lesson from this part of the talk would be we need to be mindful that LLMs are primarily trained to generate fluent-sounding language, and that's what we train them to do in pre-training. And they're also trained to satisfy users' requests, which is basically the goal of instruction tuning and reinforcement learning from human feedback. These are the main two things that they're trying to do. This list does not have, citing legal briefs correctly on it. There's not a good sense of factuality in these things yet, so we have to be very aware of that. But I don't want to be too much of a downer because these things can be super useful. Otherwise, we wouldn't all be here. I think a lot of us are probably interested in them and have already gotten some good value out of them. So far, we've kind of briefly touched on two possible ways to customize LLMs. So fine-tuning is one of them and prompting is the other. Here's sort of, I want to go through the pros and cons of them. Fine-tuning can have smaller hardware requirements. We might not need a ton of GPUs to be able to fine-tune a language model, whereas if we want to prompt a language model, probably need a bigger one, one that would have like a lot larger hardware requirements. Meanwhile, fine-tuning, because of the smaller hardware requirements, it's more feasible, usually, that we can host these LLMs locally on our own machinery, which is private. If you have sensitive data, it's more flexible, and reliable. You're not connecting to someone else's website to use it. And then on the other hand, the best LLMs that you might want to prompt are behind proprietary APIs. And the issue with that, I guess, is you're sacrificing privacy. You have to send your data to ChatGPT or something like that to be able to use it. And they might be using, who knows what they're using your data for. But then I guess another thing too is we also would depend on the service provider to always have their website or the API available. In fact, ChatGPT is kind of constantly updating their language models, and sometimes the people are complaining on Twitter this week that GPT-4 is suddenly really lazy. I haven't experienced that myself, but it's like because they're constantly changing things, it becomes harder to you kind of have to rely that this thing is always going to work pretty well. Another good part about fine-tuning is that we're optimizing for a specific task, whereas for prompting, you kind of might need to do some prompt engineering to really get a general-purpose language model to give you exactly what you want. And I think a lot of you have probably experienced this when you log into ChatGPT and ask it a very simple question, and it writes like 2 pages, right? That's not always what you want. Then on the other hand, fine-tuning is probably going to take you more technical skills and engineering effort to physically train your own model, whereas prompting has this user-friendly language-based interface, which is almost as simple as like a Google search bar. Fine-tuning also will take a large amount of training data to really adapt a smaller language model to your task, whereas prompting, you might not even need training data. You have this general-purpose assistant. Lastly, fine-tuned models are hard to adapt once you train them. If I've trained this model already on a lot of data and I suddenly have a slightly different requirement, I might have to retrain it. Whereas if I'm prompting a language model, I can just update my prompt a little bit, and I can get it to work. So depending on your specific resources and your specific needs, you can kind of choose which method to use to customize your LM. And we'll dig a little bit deeper into both of them. So next we'll talk about fine-tuning. This is kind of, if we want to look at sort of a diagram of what is a language model doing when I fine-tune it, here's an example. I want to cover a few common task formulations here where you might apply LLMs. Now the details of exactly how this interface between a task like sentiment analysis and sort of the LM itself will look different based on the model, but I just want to give some high-level ideas. So say we're doing a text classification task like sentiment analysis. We're trying to predict whether some text, like a movie review or a tweet or something like that, we want to identify whether this is a negative or a positive sentiment. So what we could do is just pass this text into the language model. Language model can give us some kind of vector representation, whether it's just an encoder, decoder, it can give us something. Then we can put a classification layer on top of that, which will turn the vector representation of this language into just a probability distribution of positive versus negative. And anyone who does machine learning, I guess you would know that now I can take that and compare it to what is the ideal sort of distribution. Like, I really want this to be labeled as positive. And then I can train the whole model based on that objective of saying, yes, this is a positive text. That's some ideas on how this will look. We'll actually play around with it hands-on as well, so I don't want to spend too much time. Another thing is, say I want to do some kind of multiple choice task, like completing a text. Here's an idea of how you would do that. Say I have some text and I need to fill in a blank. I have 2 choices. One way I could fine-tune a language model to this task is by converting all of this into 2 completed texts, and then training the model, yes, this is the correct one, this is the incorrect one. Or I actually got that backwards, but anyway, this is the incorrect one, and this is the correct one. Similarly, if I'm doing like multiple choice question answering, it looks kind of similar. Like if I want to ask the language model, how many legs does some animal have? I can train it on all these different choices and say, well, yes, 6 is the correct answer. So let's optimize for that being the correct answer within this architecture. Token classification is another task. Say you want to do part of speech tagging or named entity recognition or some kind of labeling within a text. I think you all probably would know more than me what kinds of tasks in this form you would want. But in this case, we'll look at part of speech tagging. What we can do is we'll have a representation of every token, a vector representation of every token, and learn to classify it based on its part of speech. For example, dog is a noun, and we want to optimize the model to say dog in this specific sentence is a noun. Now, text generation is sort of more general purpose. Say I want to fine-tune the model to generate text. Like, say I want to fine-tune on some specific translation task, maybe on a low resource language that this model doesn't already know about. What I can do is kind of just break this down into tokens. Again, they'll all have their own representations. We can train the model to predict, okay, after this word, the next word should be bank. Kind of just, this is just what fine tuning would look like if you want to do more language model-like training. Okay, another thing is parameter efficient fine tuning. So we've talked about, yes, we can build extra layers on top of these LMs and fine tune them. But the problem often becomes, as I've already alluded to, is you might not have enough hardware to train the best model you want, or maybe you just want it to run a little bit faster when you're training the model. So I guess I'm already spoiling this whole slide, so that's okay. But basically, I think updating all of the weights of the LM, which is what we do in fine-tuning, we update this whole thing from top to bottom when we're trying to adapt it to some specific task. That can be expensive and inefficient. So this creates a need for parameter-efficient fine-tuning methods, or PEFT. So one common way that we're going to play around with today is low resource adaptation. In low resource adaptation, basically the idea here is instead of updating all the weights for the LM, let's learn a weight update matrix, and we'll call it delta W. So we have our pre-trained language model. We just want to learn what do we have to do to these weights to apply it to our specific task. But more specifically, what they do is they want to approximate this delta W, how we have to change the weights to apply to some specific task. We want to approximate it through a matrix decomposition, A times B. So instead of using this one big matrix, we want to basically learn it as the sort of outer, is that outer product? I don't know, I'm not going to remember right now, but of these two matrices. Thus, you're learning a few less parameters. Say your language model has 1 billion parameters, maybe you're only having to learn like 600 million parameters instead, because you're doing this sort of approximation of how you're going to update the weights to adapt to your task. So what's nice about this, if none of this made sense, at least what you can take is what's nice about it, is you can train your model faster if you do it this way, and you can also do inference faster. Once you want to deploy your model, you can pre-compute this delta W, and now your model is like the same number of parameters as it was when it was a pre-trained language model without any updates. So there's some advantages to this. And also, since you have fewer parameters to learn, the possibilities of what kinds of GPUs you need or how big of a language model you can put on your GPU it's better. So you can probably train bigger language models given some GPU that you have. Now let's dive into prompting. So prompting, just I guess as a reminder, is sort of this idea that we can just interface directly with the language model using text. This is how you interact with ChatGPT on OpenAI's website. You type in and it types something back to you. So this also has some tricks that you might use to adapt to your specific task. So I guess what we're going to call this process, what we're going to call these tricks are prompt engineering. In order to customize your LLM for your specific task, you need to do some prompt engineering, and this might involve choosing a prompt template. This might involve choosing an answer mapping, I'll call it for now, meaning basically, say you have what the language model generated, how do you turn that into something useful for your specific task? And then there's also this idea of in-context demonstration that we already talked about briefly with translation. Like, we can actually demonstrate tasks to these models and they'll do it better. So let's talk about these different things. I guess let's quickly remember, though, that LMs can be used to generate language and also judge the probability of sequences of language. That's what they are at their core. This is one of the first slides I showed. So remembering that they do have this sort of probability model underneath them, let's talk about how do we apply them. How do we apply them with prompting techniques? So Uh, the problem is, I'm going to talk a lot about different NLP, language processing, AI types of benchmarks for language models. Your specific task might look very different from what I'm going to show you, but I'm hoping this gives you some tools to decide what do I need to do to apply them to my specific problem. So the first type of task I'll talk about is named entity recognition, which is a task where we want to determine, given some entity like Paris and Mike went to Paris, what type of entity is that? Is that an organization, a location, and so on? If we want to prompt engineer this to pass it into something like ChatGPT, what we could do is use a template where we say, okay, first give the sentence, then say, Paris is a blank entity. And we can evaluate the probability of location filling in this Z blank or organization or person name. And ideally, location is the most probable thing under this underlying probability distribution. We might also look at reading comprehension. So say we have this news headline about a tennis match, and we want to understand, I don't know, we have some question about this article. We maybe have to fill in a blank doing it. So for example, we have some context about this tennis match. Then we have a question about, okay, who hit their stride at the end of the match? Again, what we can do is just have like a template. Insert this context at the beginning, then ask a language model, okay, here's this sentence. If I fill in the blank with Daniela or Venus, which is more likely under the model's probability distribution? And honestly, I might even be making it too belabored. If you're just going to use something like ChatGPT, you can literally just ask and it will give you a response. But I'm also trying to focus on this idea that you might want to run some empirical experiments at scale. So digging into the probabilities is like the best way to do that. So I guess I'll quickly pause for questions. I want to wrap this up soon so we can get into hands-on. Any questions? Yes.
By saying, okay, this is missing and that is missing and so on. And so how do you sort of work around that?
Right. So correct me. I think so. I think the question is about prompt engineering in the way that I'm showing now can also be kind of achieved by doing this sort of iterative interaction with a language model. Like, I know I've seen a lot of memes this week about people playing around with DALI 3 in ChatGPT and saying, make this image more something, more.
Yeah, exactly.
It's like a meme right now.
Mm-hmm.
So by doing that, yes, I think this is kind of a prompt engineering because what's happening is some kind of in-context learning. First, the model gave you something and you said, this wasn't quite right. So then it gives you something else. And from this whole language interaction context, it can learn something from that as well. And I'll go over sort of some ideas on how can you take advantage of in-context learning in language tasks as well. But yeah, definitely. So this is one way. And really, if you're using ChatGPT, interaction is also a great way to kind of get the model to output exactly what you want.
Understood.
Cool. So yeah, let me see. I guess there's several possible tasks we can prompt engineer for, like sentiment classification again, question answering. Oh, I thought I had another here. Question answering. And basically, these all will have their own little templates. Say, if we want to do question answering with a language model, let's pass in this prompt, question, colon, give a question, answer, colon, what is it? So if you want to do this in a systematic, empirical way, you might prompt the language model 4 different times with 4 different answers, and then see which one is the most likely. If you're using ChatGPT, you might as well put all of this into the language model. But some ideas, basically, all I'm trying to show you here is like, how can you convert different types of tasks into like a text-based prompt? So let me see. You might also want to use like like more generation forward tasks like summarization or translation, like we've already talked about a little bit. Like, say I have some long text. I think this was about the summer faculty workshop. You could actually just put the long text into ChatGPT, into your language model, and say something like summary or TLDR, too long, didn't read, and it can output something shorter for you. So that's one thing you can do. Also, if you want to do translation, you might use a prompt like this. You might say French, French sentence, English, English sentence. So some ideas of how to convert these tasks to text. Now, I guess this can be important too, is like, how do you find the best template and the best answers? Because different prompts can yield different results, and it might take some extra work to find the best prompt. This could take trial and error. This could take interaction with the language model as well. Like, that's also a type of trial and error. You might want to also ensemble multiple templates if you're using like a smaller language model that isn't quite as good at this interaction. Like, say I want to judge the sentiment of the sentence, I love this movie. I could have like 5 different templates of different ways to express that to a language model, and then calculate the probabilities of all the possible sentiment labels that we might have. And once we have all this, why not just aggregate all of these outputs and determine, okay, it seems most likely that this was a great movie. This is one way to do it. Do like a majority vote or something like that. Another way to do it would be just sort of average all these probability distributions. Another way to do it could also be, you know, if your model is generating one of these words, you also might have a different space of class labels you have to map these words to, like positive or negative, right? Good and great are positive words, bad and awful are negative words. So one thing we can also do is just specifically ask the model to generate one of 3 words that's connected to our specific sentiment classes. And if you can do that, if you can dig into the probabilities and see which of these 3 words is more likely, that's another way you can kind of extract these answers from the model and systematically solve some task. So yes. And then I guess another thing you could do too is just have multiple possible words mapped to classes. It doesn't have to be one-to-one. Basically, the goal is you want to have a way to turn whatever the model generates to something meaningful for your problem, like a label for sentiment. Another thing that's important, and actually we'll talk about this a bit more, is that LLMs use randomness in generating language to some degree. This is why when you ask ChatGPT something, it will output something different every time. And some solutions to this would be, well, we could generate multiple times and just average the results. You could also use what's called greedy decoding. Usually, like if you're using like the OpenAI ChatGPT API, there's a parameter for this that I'll also show you in our hands-on part, where basically use no randomness. Just always choose the most likely word to be the next word when you generate language. So we're a bit familiar with in-context learning. We can show examples and models more likely to pick up our task. The last thing I wanted to cover for this chunk is chain of thought prompting, which is like a special in-context learning trick. So for some language tasks, the output could require multiple steps of reasoning, like say we're trying to solve math story problems, for example. If I just prompt a language model directly, even if I give a few examples first, like I give one math problem, then ask the language model to do another math problem, language model probably cannot get this because language models are not trained to do mental math. So what you can do instead is provide some reasoning explanation in your in-context demonstrations. For example here, let's give a few math operations on what you have to do to get the final answer. And then once you do this, the language model can also follow suit, generate some rationale, and then give you a final answer. So if you have some complicated multi-step task, this is the sort of trick you want to use. And there are a lot of twists on chain of thought prompting. One twist was people also found you don't have to come up with the chain of thought yourself. You can just ask the language model to let's think step by step, and it will generate some kind of explanation like this. And then you can use that, prompt the language model again with that explanation, and let that inform the generation of the final answer. So we were really amused in NLP when this was a new development. It's like you just ask the language model to think step by step, and suddenly it's smarter. But yeah, there are also a lot of other twists. There's like so many papers coming out of our field about different ways to do this chain of thought prompting. But I think if you can get this sense of, the way you demonstrate the task, the types of steps that lead up to it, and that actually can affect your output significantly. If you can get that, that gives you a really good tool when you're trying to apply these LLMs in your own tasks. That is it for the first part. I guess I'm going to shamelessly plug that I'm on the job market for academic and industry positions. You can find me here, and I think maybe we'll break for questions, maybe take a break. I don't know what the plan is, but we'll move on to hands-on stuff shortly. So thank you.